Hey folks, welcome to the SAS Lab for Chapter 8. All right, so this is lab number 8. Let's see, you got a few things to do here. So let's just get going on this. All right, the learning lecture, the learning objectives. Good grief, I'm having such trouble with my language today. Anyway, the learning objectives. Conduct a single sample hypothesis test, and we're going to do that using the Proc t-test procedure in SAS. All right, and then from that, I want you to do two things. I want you to be able to create a table of results, and then also correctly interpret the results of the test. All right, so create a table of results. So this is going to show the results from the of the t-test. It's going to give people information about the sample mean and things like that. But it's also going to show results of the t-test. And then I'm going to essentially walk you through the interpretation of the results. And in both, and, when you get to this section, you're going to say, well, what we're doing here is a little bit redundant. But it's on purpose that I do that because, for your, if you guys go on to take more courses in stats and research methods and you're writing papers, having to use, software like SAS or, things like that, one of the things you're going to have to be able to do is to summarize the results of your study. Right, and you want to be able to do that by creating a table that shows all the results in some nice, concise format, and or writing out the results again in some nice, concise format. All right, so here's going to be a little bit redundant, but what I want you to focus on is just the act of taking results from a hypothesis test, putting it into a table format, and then coming back and taking those same results and putting it into a written format. Okay, I just want you to get practice doing those two things. Okay, all right. So in actuality, you wouldn't create a table and then write out stuff that repeats exactly what's in the table, right? But just to give you a little bit of practice doing that. Okay. What else we got here? All right. So the key terms, alpha level. Yeah, right. So the stuff that we've talked about in the lectures. All right. So what we're going to do is, pretty simple. We're not going to do a whole lot of programming here. We're going to create a data set of 100 people. All right. Now this is what I came up with. You can either run this same simulation or you can come up with something different. Okay. So I created just a simple data set of 100 people. All right. These are simulated people, so this is not being drawn from any real data source. Okay. And then I created 4 quantitative variables, right? So remember, the t-test uses quantitative variables, so interval or ratio variables. All right, and then I said, all right, well, these 4 quantitative variables represent college subjects. And so what I wanted to do was to think about, in this general sample, right, of 100 people, what would the grade distributions look like in 4 different college subjects? All right, and again, if you wanted to go with college subjects, but you didn't want to, do the same ones I did here, just choose a bunch. Or, as far as I'm concerned, you can just make up some college subjects. Like, I don't know, how would people do in a course of basket weaving? Right? And then, after you sort of imagine how well or how poorly your sample would do, in each of these subjects, what you want to do is then use the rand normal function in SAS to create these variables and, set the conditions for their distribution, so the mean and the standard deviation. Okay. All right. I think we got one more page here. Yep. So after we, set up the data, the first thing we're going to do is run a statistical power analysis. Okay. And then we're going to run a hypothesis test for each variable. All right. And like I said, we're going to use the Proc t-test procedure. Then we're going to write and interpret the results of each hypothesis test. And then after you're done with all this, just submit a copy of your SAS code, submit a copy of the table of results that you create, and then submit the written interpretation of results, and just put that all into the Dropbox for Lab 8. Okay. All right. So let's see here. So like I said, the SAS program is pretty easy setup. You've seen this kind of setup many times already in the semester. All right. Again, there's nothing special about this, this data set name. I'll just say data perform, call stream init to give SAS an initial value to start creating these random variables. I chose 1949 because Long Beach State was founded in 1949, right? 49ers, that's where it comes from. All right, so anyway, again, I set up I just create a small sample, 100 people. And so the 4 college subjects that I chose were physics, stats, art, and American history. And again, you can run with these same ones or do something else, okay? All right, and so for physics, I said, all right, well, the average for my sample of 100 people would probably be around 50 with a standard deviation of 10. All right, so, again, why am I setting it at 50? Just because. All right. Physics is typically seen as a very difficult subject, and, people tend not to do that well in it, at least in their first course, blah, blah, blah. Okay. So it doesn't, there's no magical reason why I put, 50 and 10. Okay. But you just want to think about it. You just want to think, well, how do you think they would perform? That sample of 100 people, in your data, I mean, how do you think they would perform in a course like physics? All right. And so whatever you think, however you think they would perform, you just put in values into the rand normal function that would correspond to, what you think is going on. Okay. So no magic numbers here, okay? All right. For statistics, all right, I'm thinking, all right, well, 99 on average, right? So these folks are going to be, pretty hot stuff in statistics, right? And most of them are going to be right in that same range, right? So you got an average of 99 with a standard deviation of 0.1, all right? So almost everybody is right there together, okay? And then for art, we have something more of a, a little more variation there. Average is 74 with a standard deviation of 2 in American history. The average is 85, also with a standard deviation of 2. Okay, so again, folks, the right numbers are, are the ones that generate the distributions that you think you would see. Okay, all right, and that's all there is to it. Okay, that's all there is to it. Okay, all right, because again, it's so important that that you're able to think about data, think about it in terms of a distribution, and be able to recognize that distribution, right? Um, at some point you'll be able to take a look at a distribution and say, okay, well, I know exactly what's going on in there. I know exactly what's going on in that distribution. Okay, right? So, and that's, like I said, that's the hardest part of, doing some of this work, right? Being able to imagine what a distribution looks like. All right. Let's see. All right, and then for our power analysis. Now, really, I could run a power analysis for each of the variables. All right, but basically, I set this up. So I told SAS, okay, I want you to run the analysis, run a power analysis for a one sample means test. All right, and so we're looking at the t-test. So it says one sample means, and then for the test, and again, like I said, there are a lot of different tests you can run. All right, we say for the test, we want it to run a t-test. Okay, so we simply put t there. All right, and now what the mean that we want to set as the null is 75. All right, because if a class, if a pretty much in every class, a perfect normal distribution in grades, if you're thinking about like a 50 to 100 or something range, all right, it would settle out probably around a 75. Okay, the mean would probably settle out around 75. All right, so you have like a mid-range C. Okay, all right. And roughly the standard deviation is 10. All right, now notice for the mean, right? So I have the null mean equals 75, and then that next line, mean, I have just a period there. All right, so I'm telling SAS I want it to calculate the mean that I would need to observe in order to reject the null, which says the mean is 75. Okay, so what mean would I have to observe given a null mean of 75 and a standard deviation of 10 with a sample size in total of 100? Okay, what mean would I have to observe in order to reject the null? Okay, all right, now that last one, that last line there, power equal 0.95. All right, so I want SAS to give me a mean that not only allows me to reject the null, that I would need to observe to reject the null, but I can reject the null with about 95% confidence that I am not making a type 1 error. Okay? All right? So I want to be able to say that, all right, since I observed a value of this or something larger, I can reject the null that the mean is 75, and I can be about 95% confident that I'm not making a type 1 error. Okay? So I'm not rejecting the null, but, or I should say this, I'm not looking at a false positive result. All right? So I'm not looking at a result that says, well, yeah, I can reject the null, but the null is in fact true. Okay? All right? So I want SAS to set the conditions so that if I can reject the null, I can do so with 95% confidence that I'm not committing a type 1 error. Okay? All right, so for the SAS program, for the Proc t-test, again, I set this up. I set up something very similar to this in the lecture in part 3, right? So Proc t-test, data equal perform, So referencing the data set that I just created, all right, the null hypothesis, HO is equal to 75. I want a two-tailed test, right? And I want the alpha at 0.05. Now that last option that I put in there, CL confidence limit, all right, so I want SAS to create a confidence limit around each of the estimates from my sample, okay? All right, and I want to see if that confidence limit contains the value of 75, okay? Because if it does, that means that I cannot reject the null hypothesis. So if that confidence limit that I've created contains the value of 75, I cannot reject the null hypothesis. I can only reject the null hypothesis if that confidence limit does not contain the value of 75, okay? All right, oh, and then for the variables, all right, so I have 4 variables, all right, and if you remember, I created the variable physics first and American history last, all right. So at this point, I don't have to write out each of the 4 variable names. I can just list the first variable, followed by 2 hyphens, dash, dash, followed by the last variable in the series, okay? All right. So SAS will automatically read that series and say, all right, well, I start with physics and go, you know, and take every variable until I get to American history. And that will be, American history will be the last one that it uses. Okay. Let's go to the next one. All right, so here's the output from the Proc power procedure, okay, from the power analysis. All right, and I see one mistake that I made already, okay. So in the power analysis, in the previous slide, I said the power analysis is set to 95, so power would be set to 0.95. So here I set it to 0.9. I can't remember why I changed that, but anyway. Okay, I changed that to 0.9. All right, so with the power analysis I have here, it says that, you know, given a null mean of 75, a standard deviation of 10, a total sample size of 100, and a 90% chance of avoiding or not making a type 2 error, or a 90% chance of avoiding a false positive result, and a two-tailed test with an alpha of 0.05, right? So under all these conditions, right, I would need to observe a mean of at least 78.3 in order to reject the null hypothesis, okay? In order to safely reject the null hypothesis, okay? All right. So in other words, I would need to see a mean of 78.3, right, or 3.3 points above the null mean, or 3.3 points below the null mean, okay? So I can see it I can observe it in either direction, but it has to be at least 3.3 points away from the null mean in order to reject the null hypothesis, okay? Again, with a 90% confidence that I'm not committing a type 1 error, okay? So before we dive into too far into the t-test, we want to make sure that our variable that we're using in the t-test meets the assumption, or meets the assumptions of the t-test. So it's, we know it's from a random sample. We know it's an interval variable, and so it's quantitative variable. All right, but we need to make sure that it's normally distributed. okay, or at least, approaches normality in its distribution. All right, so like I said in part 3 of the lectures for chapter 8, when you run the Proc t-test, right, it'll give you the t-test results, but it'll also compare your variable to a normal distribution. So we'll start there, and then we'll go to the actual t-test results. Because if the variable doesn't meet the assumption of normality, then we're not really clear on what we're supposed to make of the results. Okay. All right. We might be looking at some sort of bias in our results. All right. But here it looks like we're pretty good. All right. So this is just for the variable physics. I ran it for each one. All right. But this is for the variable physics, and all of them are normally distributed. All right. So looking at our histogram, right? The histogram represents our actual data. All right. So this represents the actual data for the variable physics. All right. And then the two lines you have here, the blue line represents a perfect normal distribution. All right. The red line is what we call a kernel distribution. All right. And so that's going to follow the histogram a little more closely. Okay. But what our main concern is the blue line. Okay. So it looks like most of the histogram fits within that blue line. All right. Anywhere it falls outside the blue line, represents deviation from a normal distribution. Okay, but it looks like most of ours is inside the blue line. So and there is some deviation, but not much. And then we also want to take a look at the QQ plot. And again, this is generated by the Proc t-test procedure. All right, and like we talked about in part 3 of chapter 8 of the lecture for chapter 8, each point here, each data point, each circle represents one of the people in our sample, one of the simulated people in our sample, right? And the straight line represents a perfect normal distribution. Okay, so if all these data points fall along this line, that means that we're looking at a perfect normal distribution. So we can see that they're pretty tightly clustered around that that straight line, right? There is some deviation from it, though. Okay, so it's not a perfect normal distribution, but it's pretty close. Okay, it's pretty close. All right. Ideally, we want it to be a perfect normal distribution, but in reality, we typically only deal with pretty close, right? But again, you want to remember that the t-test is robust to violations of some of these assumptions. You don't want to do any sort of wholehearted disregard of the assumptions, but you want to make sure that your variables are at least fitting, that your variable satisfies to a significant degree the assumptions of the t-test. Okay. What's next? All right. So now that we're satisfied with our variable and how well it fits the assumptions, all right, we can then move on to the t-test results. All right. So the t-test procedure doesn't kick out a ton of data, right? But there's still, quite a few numbers there you have to kind of make sense of. All right. All right. So looking at the the last table here, okay, this tells us everything. All right. So again, this is for the variable physics. All right. So the t-test results tell us that this mean for the variable physics falls 21.38 standard errors below the mean of 75. Okay. All right. So that's a pretty large difference, right? That's a pretty large difference between our mean and the null mean of 75. Pretty large difference there. Okay, but then what is the probability of that the mean that we observe for physics would be found in a distribution where a distribution of random error in which the mean is 75? What's the probability of observing our mean in that null distribution? All right, well here, again, it's a very small probability, right? So it's less than 0.0001, or, as I have over here, right, the chance of our sample, or the mean for physics occurring in a distribution of random error in which the mean is 75, is only, 0.01%. Okay, so 1/10 of 1%. And so pretty small, right? Pretty small. Okay. I'm sorry, 1/100th of 1%. Sorry about that. Good grief. All right. So pretty small. All right. Okay, so like I said, it's important that we're able to, develop nice summaries of our findings. Okay, and a nice table is one way to do that. Okay, so here we list the, again, change this heading as, to fit, your examples. Okay, so since I was looking at academic subjects, all right, I have a column representing academic subjects. So I have physics, statistics, art, American history. Okay, so then I report the mean and standard deviation for each of those variables in my data. Right, so the mean of 51.5 for physics with a standard deviation of 10.99, statistics 99.01 as a mean and 0.08 as the standard deviation, so on and so forth, right? All right, and then I also want to, report degrees of freedom. Okay. All right. So for my degrees of freedom for each variable, 99. Okay. And then I want to report my t-value for each one. Okay. And then the p-value for each one. All right. So let's just go through this. All right. So with a mean of 51.5 and a standard deviation of 10.99 and degrees of freedom of 99, my t-value, all right, my calculated t-value is negative 21.38. So again, that says that this mean of 51.5 falls 21.38 standard errors below the mean of 75. Okay. Right? And the probability of observing this mean of 51.5 in a distribution of random error, right, in which the mean is 75, is less than 0.01. Okay? So I could have put, 0.0001 here, but, really, folks, what you'll see in research studies that are being, published in journals, they won't go to that extent. They'll just say it's less than 0.01. Okay, and so the same point is being made. Okay, all right, so it's really small. So in this case, I can reject the null, right? Because there's only like a 0.01 probability of the null being true. So I can reject that and say, all right, well, it's very unlikely, highly unlikely, that I will observe a mean of 51.5 in a distribution of random error. Okay? Highly unlikely. All right? So, again, what does that mean for, these 100 people? All right, well, it means that, you know, there's probably no one in this group that should try to pursue physics as a major, right? You should probably want to stay away from that. By contrast, everybody in my, every one of my 100 simulated people should probably pursue a major in statistics, all right? Because they score way above the mean of 75, okay? And look at the t-value, all right? So collectively, this group, this mean here, 91.01, is 2,955 standard errors, all right, above 75, which would be the mean expected in a distribution of random error, okay? So, again, there's less than a probability of 0.01 of observing this mean in a distribution of random error, okay? All right. For art, we have 73.68 for a mean, standard deviation of 1.9, DF of 99, all right? And this mean falls a little bit closer to the mean of 75, but it's still, different enough for us to say that, well, it's probably unlikely that we would observe a mean of 73.68 in a distribution of random error in which the mean is 75, all right? So it's closer than these others to the mean of 75, but nevertheless, it's unlikely. It's unlikely that we would observe this value in a distribution of random error, okay? Same thing here with American history. The mean is 84.93, the standard deviation of 1.84, and degrees of freedom of 99, right? The t-value is 53.94, and again, that means that this mean of 84.93 falls 53.94 standard errors above the mean that would be expected in a null distribution, okay? And once again, we can reject the null, right? So as long as these values here are 0.05 or less, all right, we can reject the null hypothesis and say that it's far more likely that these means and standard deviations, that these means came from distributions that are not the result of random error, okay? All right. Let's see. Like I said in part 3 of the lectures for chapter 8, typically you'll just show either a table or write out the results, okay? You typically don't do both, right? But like I was also saying, I want you to do both here just to kind of get in the practice of it, okay? Just to have some practice doing, both methods of presenting the data or presenting the results of your t-test. Sorry about that. Okay, so if you take a look at the writing, it's not very creative writing, right? It can be, but typically, when you're doing research and you're reporting the results of statistical analysis, you typically want to be pretty straightforward. Don't try to use very sophisticated language. Just keep it pretty simple. Okay. So like you see here, study participants for physics. All right. Study participants reported grades in physics. The first thing we indicate here is the mean. All right, which is 51.50. Standard deviation of 10.99. Right? And we say that that is lower than the average of 75, which of course represents the null distribution. All right? And then after we make that statement, we follow it up with a simple statement about what we found in our t-test results, okay? All right, so we have T. This indicates to the reader what particular type of hypothesis test we use. 99 represents the degrees of freedom. All right, and then they can see here and say, all right, well, this mean of 51.5 falls 21.38 standard errors below 75, okay? And there's only a very small probability of observing a mean of 75 in a distribution of random error in which the mean is 75, okay? All right. The next one, okay, again, reads pretty much the same. Study participants reported grades in statistics, and followed by the descriptive statistics here, right? Higher than an average of 75, followed by details of the t-test, okay? And so again, someone who's reading this, all right, can, take a look at the results, okay? And say, all right, well, then it looks like for each variable here, physics, stats, art, and American history, it looks like this group of students, this group of simulated students, right, were either below average, and in some cases well below average, or above average, all right, in these different subjects, okay? And so again, where would you go with this? All right, well, think of yourself as, again, a counselor of some sort. And you're saying that, well, it looks like this group over here is struggling in stats, or is struggling in physics, but they do really well in stats, and so maybe they should, think about a stats major, okay? Think about, you could probably do this for yourself, where you could, compare your grades in mathematics, right, and all your in all your mathematics courses, and compare it to an average of 75. Calculate the mean standard deviation, and then, run a t-test, okay? And if your average grades in math are above a 75 or well above a 75, all right, maybe take a shot at physics. Take a shot at statistics. As majors, okay? Right? But there's there are some important ways we can use this information that we see here to make some decisions about, well, in this case, choice of major, okay? All right, now, one thing before I leave this slide. The way you see the information about the t-test written here, M italicized, capital M italicized, capital SD italicized, and the way the details of the t-test are written out here. This follows the APA format of reporting t-test results, okay? So APA is the American Psychological Association. Okay, and it's just one of probably 100 different ways different disciplines would, report the results of some sort of hypothesis test, okay? All right, but whatever discipline you're in, right? So for my psychology majors, you want to become familiar with this this format of reporting, at least the results of a t-test. This is how you would report the results of a t-test in psychology. But again, even within psychology, there are a lot of different journals, and so some journals in psychology might use a slightly different format or whatever. But you just need to be aware. You just need to be aware of what format you need to use to present your hypothesis test results, okay? In sociology, for my sociology majors, sociology has its own format for presenting these results, but again, there are many different journals within sociology. Some of the journals actually use the APA format. Like one of the top journals in sociology actually uses the APA format. It doesn't use the what's called the ASA format. ASA is the American Sociological Association. Fun fact: when the American Sociological Association started out, it was actually called the the American Sociological Society. And you can kind of see why that became problematic, and they decided to change it to ASA, right? But anyway, you know, ASA has its own format. Other journals in sociology have their own format. Okay, and so you just want to become familiar with those, all right? Because I will tell you, all right, whatever field you go into. Computer science, sociology, psychology, finance, whatever field you go into, formatting of any papers that you write, formatting for any hypothesis test result you report, very important. And if you screw up on that, you could very well get an F for the paper. Okay, everything else could be perfect about the paper, but if the formatting is all screwed up, you're probably going to get an F. Okay. All right. So it's taken very seriously. Okay. All right. What else do we have here? All right. So again, the interpretation, I've already, given this, but the interpretation can be this straightforward. Study participants in the sample performed significantly below average in physics and art. The grades in statistics and American history were significantly above average. So they did much better in statistics and American history than they did in physics and art. Okay? So, again, where do we go? Well, maybe we want to push this group of students into, if they're thinking about physics and art as majors, maybe push them towards statistics and American history. Okay? All right, so remember, this is all about, we're doing all this to help us make a decision about something. All right, whether it's the quality of our data or making a decision about, what would be the best action to take in some situation. All right, so that's it for SAS Lab 8. So, just run through that. And again, you can either do exactly what I did here, use the exact same variables, use the exact same numbers, right? Or you can, change those up. And again, I strongly encourage you to just change it up. If you don't, you won't be penalized, all right? If you do change it up and, you kind of mess up a little bit, I'll look past that. Because it is, the fact that you took a shot at it on your own is a valuable experience for you, and I don't want to discourage you from doing that. Okay. All right. So to wrap up all this, chapter 9 is coming up next, and so that's going to be really short. Okay, because we're working with pretty much the same principles that we just covered in chapter 8, but we're just applying it to a 2-sample t-test rather than a single sample t-test like we did here. Okay, so there'll be a quiz. That quiz is going to cover chapter 8. All right, and then there'll be a gear project where you conduct a single sample t-test and a 2-sample t-test. All right, and you give a quick write-up of the results and you turn that in. Okay, but this, after the gear project, that's it. That's it for the semester. All right, that's the last thing. Okay, so there's nothing else coming after. There's no more lectures after Chapter 9. Okay, so Chapter 9 is it. No more quizzes after the quiz for based on Chapter 8. And no more gear projects after this one. Okay, so that's it. All right, and again, folks, let me know if you need some help on this lab, if you need some help on, even if you haven't gotten started on any stuff for the class yet, just let me know. I'll help you out, okay? And I won't judge you. I won't say, oh, why'd you procrastinate? Screw all that. You need help. I'm here to help you. Just let me know, okay? All right. I will see you then.